Welcome. Today we're stripping back the Cambridge IGCSE Physics syllabus to see how the universe talks to itself through energy. At the heart of all physics is energy and interactions. Our study is divided into 6 interconnected modules that show how energy moves through our world. We start with the macroscopic world in Module 1, covering motion, forces, and energy. From there we dive into the particle world with thermal physics, then explore energy and motion through waves. Module 4 examines the flow of charge in electricity and magnetism, followed by the subatomic world of nuclear physics, and finally, we look at the cosmic scale in space physics. Theme 1 focuses on mechanics. There are 3 fundamental formulas to master here. Speed is distance over time. Acceleration is the change in velocity over the change in time. And Newton's second law, which states that resultant force equals mass times acceleration. Look at the anatomy of forces schematic. For any object, like this car, we must account for driving forces, resistive forces like friction and air resistance, weight, and the normal reaction force. Remember Newton's first law. If these forces are balanced and the resultant force is 0, the object will remain stationary or continue at a constant velocity. Continuing with mechanics, we look at collisions and energy stores. In a closed system, total momentum before a collision always equals total momentum after. We define momentum as mass times velocity, while impulse, force times the change in time, explains car safety features, like crumple zones, that reduce force by increasing the time of impact. On the right, the energy store matrix defines kinetic energy, gravitational potential energy, and work done. Finally, power is defined as the rate of energy transfer, measured in watts. Theme 2 moves into the particle model. Matter exists in 3 states. Solids are tightly packed regular lattices. Liquids have an irregular arrangement where particles slide over each other. And gases consist of widely spaced particles in random rapid motion. Gas pressure is specifically created by these particles colliding with container walls. We also define absolute zero as 0 Kelvin, or minus 273 degrees Celsius, the point where particles have minimum kinetic energy. To heat a substance, we use the specific heat capacity formula to calculate the energy required to raise the temperature of 1 kilogram of a substance by 1 degree. Energy is transferred thermally in 3 ways. Conduction occurs through lattice vibrations and the movement of free electrons, making metals the best conductors. Convection happens only in fluids, liquids, and gases, as heated fluid expands, becomes less dense, and rises. Radiation requires no medium at all, traveling via infrared electromagnetic waves. Note the material impact. Matte black surfaces are the best absorbers and emitters of radiation, while shiny silver surfaces are the best reflectors. Theme 3 introduces the wave model. Every wave has a peak, a trough, an amplitude, and a wavelength, denoted by the Greek letter lambda. The universal wave equation is speed equals frequency times wavelength. We can observe 3 primary behaviors in a ripple tank. Reflection, where the angle of incidence equals the angle of reflection. Refraction, where waves change speed and direction, usually as they enter shallower water. And diffraction, which is the spreading out of waves as they pass through a gap. The electromagnetic spectrum is a continuous range of waves. On the left, radio waves have the longest wavelength and lowest energy. As we move right through microwaves, infrared, visible light, ultraviolet, and X-rays, we reach gamma rays, which have the shortest wavelength and highest energy. Each has specific uses and risks, such as UV causing skin cancer or X-rays causing cell mutation. The universal rule to remember is that all EM waves travel at the exact same speed in a vacuum, 3.0 times 10 to the power of 8 meters per second. In Theme 4, we study the rules of circuitry. You must recognize the symbols for thermistors, LDRs, diodes, LEDs, and variable resistors. In a series circuit, current is the same everywhere, but voltage splits across components. In a parallel circuit, current splits at junctions, while voltage remains the same across all branches. Our 4 essential formula cards here are Ohm's law, V equals IR, electrical power, P equals IV, energy, E equals IVT, and charge, Q equals IT. Magnetism involves the interaction of currents and fields. We use Fleming's left-hand rule to determine the direction of force in the DC motor effect, where a current-carrying coil in a magnetic field experiences a turning force. Conversely, moving a wire through a magnetic field induces a voltage, a concept used in transformers. High-voltage transmission is essential for the power grid because it reduces current, which minimizes power lost as heat in the cables. Theme 5 takes us into the nucleus. Rutherford's alpha scattering experiment proved that the atom is mostly empty space, with a tiny, dense, positively charged nucleus at its center. We represent atoms using nuclide notation, where A is the nucleon number, the sum of protons and neutrons, and Z is the proton number, which dictates the element. Remember, isotopes are atoms with the same number of protons but a different number of neutrons. Radioactive decay involves three types of radiation: alpha, which is a helium nucleus; beta, a fast-moving electron; and gamma, an electromagnetic wave. They differ in their ionizing power and what can stop them, ranging from a sheet of paper for alpha to thick lead for gamma. We measure the rate of decay using half-life, which is the time taken for half the radioactive nuclei in a sample to decay, as shown by this exponential decay curve. Our final theme is space physics. Our solar system is divided into an inner zone of 4 rocky planets and an outer zone of 4 gaseous giants. The accretion model explains that the system formed from collapsing interstellar clouds of dust and gas. To calculate orbital speed, we divide the circumference of the orbit by the orbital period. Crucially, the rule of gravity states that gravitational field strength decreases as distance from the Sun increases, meaning further planets travel at lower orbital speeds. In this final content slide, we examine the life cycles of stars and the origins of our universe. Every star begins in a nebula, a cloud of dust and gas, collapsing into a protostar before reaching the stable main sequence phase where it fuses hydrogen into helium. The path then splits based on mass. Smaller stars, like our Sun, expand into red giants, shed their outer layers as a planetary nebula, and end as a cooling white dwarf. Massive stars, however, expand into red supergiants before a cataclysmic supernova explosion, leaving behind either a dense neutron star or a black hole. On the right, we have the 3 pillars of Big Bang evidence. Redshift shows light from distant galaxies stretching as they move away from us, proving the universe is expanding. CMBR is the afterglow of the Big Bang, cosmic radiation that has cooled and stretched into the microwave region. Finally, we use the Hubble constant, h0, to relate the speed of receding galaxies to their distance, allowing us to estimate that our universe is approximately 13.8 billion years old. As you prepare for your exams, remember that these 6 themes are not isolated. They are all linked by the flow of energy and the fundamental laws of interactions. Use these visual maps to anchor your understanding of the master equations, from Newton's second law to the wave equation and Ohm's law. Success in IGCSE Physics comes down to 3 things: learning your definitions, mastering your formula cards, and understanding the physical phenomena that govern our universe. Good luck with your revision.